The 18-hour database blackout, a GitLab postmortem, a DevOps postmortem. Every engineer has a story about a system failing spectacularly. You know the one that starts with a minor hiccup, a blip on the dashboard, and somehow spirals into a full-blown dumpster fire catastrophe. The GitLab outage of January 31st, 2017 was exactly that. It wasn't some sophisticated zero-day exploit or a massive DDoS attack that brought the lights out. It was quite literally a human error. We were dealing with a primary production database, a system holding gigabytes of user data, and the only thing standing between us and total collapse was a shaky understanding of replication and a very bad day. It's a classic case study in the fact that even the most robust, modern infrastructure can be undone by a single, misplaced command. This wasn't just a downtime. It was a massive, painful lesson in the fragility of distributed systems and the absolute necessity of redundant, tested safety nets. To understand the magnitude of the disaster, you have to understand the initial conditions. The system was under strain, and the strain started innocuously enough. On January 31st, 2017, the first sign of trouble was spammers. They were detected hammering the database, creating snippets which started to cause general instability. This initial load spike was the first warning sign, the kind of minor annoyance that gets dismissed until it's too late. As the day progressed, the increased database load on GitLab.com led directly to PostgreSQL replication lag. Replication lag is when the secondary copy of the database, the failover copy, stops keeping up with the primary. This is a critical indicator. It means the system is already struggling to keep its data consistent across multiple nodes. The instability was building slowly and steadily until it reached a critical mass. The situation deteriorated rapidly after the initial load spike. By 2100 hours universal time coordinated, the sheer database load escalated dramatically. This wasn't just slow, it caused a complete lockup on writes, which immediately signals a serious problem with database concurrency and resource contention. When writes lock up, users can't commit changes, and the service starts failing in noticeable ways. Compounding this, the replication lag continued to worsen. By 2200 hours universal time coordinated, the secondary database was lagging too far behind to be useful. A spike in writes was the catalyst, effectively stopping the replication process. At this point, the system moved from slow to broken. The natural instinct for an engineer is to intervene, to manually fix the synchronization, but that intervention, in this case, was the fatal flaw. Here is where the war story gets dark. The initial issue was technical, replication failure and high load, but the root cause was profoundly human. Around 2300 hours universal time coordinated, an engineer attempted to resynchronize the secondary database. This task, while necessary, is inherently high risk. The goal was to wipe and rebuild the secondary data directory to get it back in sync with the primary. The problem, however, was a catastrophic mix-up of servers. Instead of executing the cleanup and resync commands on the intended secondary database server, db2.clustered.gitlab.com, the engineer mistakenly executed the destructive rf command on the primary production database server, db1.cluster.gitlab.com. This command is notorious in engineering circles for its power and lack of safety checks. It deleted approximately 300 gigabytes of live production data. In a single moment, a typo or a misplaced command executed against the wrong target wiped out the heart of the service. The moment the rf command completed, the scope of the disaster became terrifyingly clear. We weren't just dealing with downtime. We were dealing with permanent data loss. The deleted data included user accounts, comments, issues, and project snippets, the core intellectual property and history of the entire platform. The initial panic was compounded by the failure of multiple safety mechanisms. We discovered that the standard PG_dump backups to Amazon S3 were non-functional, failing silently due to a PostgreSQL version mismatch. Furthermore, the Azure Disk Snapshots, which should have been a primary recovery method, were not even enabled for the database servers. The system was designed with critical single points of failure, making the recovery process exponentially harder and more stressful for the on-call team. If this saved you an outage, subscribe for the next postmortem.